Hi, BC Calculus, Mr. Ellinger here, and we're going to just crank through some notes that we didn't get to in class on Friday. Here we go. This is page 3 on the guided notes. This is in OneNote if you don't have a copy of it. So minimums, maximums, critical points, and the extreme value theorem. And the book basically covers this in 3.1, but it doesn't cover everything in it. So the big question is, under what circumstances do you know that a function has a minimum or a maximum? We're going to be trying to find minimums and maximums of functions using calculus a bunch of times. The only thing is okay, how are we going to know if there even is a minimum or maximum? And when we say minimum or maximum, remember, we're talking about a y value. Like there's a minimum or maximum y. We don't worry about minimum or maximum x's. So in class, we would draw examples of functions that do have maximums, like, oh, this function has a maximum. There is one y value that is the maximum y value. And then we could have even interesting ones like this. There's still a maximum. The y value right on the endpoint would be the maximum. But under what circumstances would we maybe not have a maximum over an interval? And so we'd brainstorm this, and there's a few things you can come up with. One is if you have a asymptote, then from 0 to wherever this is, you don't have a maximum because it just keeps going up and up and up. You can get some creative other ones, like what if you had a sine function, except at the very top, at the very peak, it was undefined, and then went back down again. Again, you wouldn't have a maximum because it would get closer and closer and closer to that number, whatever that y value is right there, but it would never actually achieve it. And so I couldn't give you, if this hole happened right at the peak and happened right at 1, I couldn't tell you a maximum y value, one number that is the biggest y value on that function over that interval. So the summary then is the extreme value theorem, which is that a function has a maximum and a minimum, but we're just going to say maximum most of the time, but everything here applies for minimums too. It has a maximum over a closed interval as long as the function is continuous over the closed interval, so over a to b. We couldn't do it for an open interval because if we did it for an open interval, you can think that, well, you could have an asymptote at the edge. It would be continuous from a to b, parentheses, but it still wouldn't have a maximum because it would keep going up. But once we define it as, we say this function is defined and continuous over a closed interval, then we can't have that asymptote because then we have to have something at the end point, at the edge. We need a y value at b, and it needs to stay continuous. And so you can have an asymptote and yet still be continuous. So in mathematical language, we'd say f of x is continuous. I'm just hammering that. If a function is continuous over that closed interval, then there's some d in a and b. So d is an x value such that every function value has to be less than or equal to the y value there. So every y value on the function between a and b is less than or equal to that one number. That's a number that you can get plugging a number in over the interval. Let me just kind of show you. So what we'd have is we'd have a to b, and we'd have some function, I'll do that. I'll leave it at that. We've got some number d, and let me pretend I curve down instead and just ignore that. We've got some number d that's in between a and b, where every function value between a and b is less than or equal to that f of d. So that's how they can say it in sort of specific mathematical terms for all x in a to b. I'm going to skip the super duper mathematical language. I'd show that in class. I like to every once in a while introduce you to really real mathematical shorthand, but we're going to leave that for now. Okay, so now you've got a few examples. And by the way, did I say it? Yeah, that's called the extreme value theorem. And the same thing would apply for minimums. I was just focusing on maximums, so I didn't have to keep saying and minimums too. All right, so you've got 3 sample problems. I'd like you to pause the video right now and try to solve these 3 problems. Some of them might be a little tricky, but do your best on them and see what you come up with, and then we'll show you the answers. So pause it, do the problems. Okay, so for the first one, the extreme value theorem, it just has to be continuous from 0 to 2 pi. So for this function, for extreme value theorem not to apply, I need a discontinuity. And so, you know, like, oh yeah, if sine was -1, so 0 to 2 pi. So at 3 pi over 2, this would make a discontinuity, so that's out. But if I look at this one right here, then everything from 0 to 2 pi I plug in for x, it's always going to be defined because the plus pi is going to bail me out. And x squared will always be positive. So I can't possibly have a denominator being 0. That's the answer. Of course, on both these, if x equals pi, it's not defined. So all I need to do is find the function that made sure it was continuous, and then I was set. Next one, this one's a little tricky. So this one says, by the extreme value, there's a value c, they use c instead of d, such that g of c is less than or equal to g of x over this interval. So first you have to look and say, is this thing continuous? Well, as long as I'm not square rooting a negative, I'll be okay. And sine x can only be between -1 and 1, and then I square it. There's no way I'm going to get a number bigger than 1 out of this, and so I'm always going to be defined, and this thing's going to be continuous. So therefore, this is what we just said, that there has to be a value c, or actually this one is the local minimum, that every function value is above that one value. And so that one says there has to be a minimum. The next one is the one we just did. There has to be a maximum such that the function at c is greater than all the other function values. So this is the extreme value theorem. And check. Now the intermediate value theorem, there has to be a value c such that g of c is equal to g of 0 plus g of pi over 2. We know this is continuous, so the intermediate value theorem does apply. And so if you think about it, whatever this function looks like, I don't have a graph of it, but whatever it looks like, I'm just making a graph, then we know that between 0 and pi, that it's continuous, can do the intermediate value theorem, and what it's saying is there has to be a spot where the y value is equal to the average of the two. So if this is g of pi, and this one here is g of 0, then at some point in time I have to achieve the average of the two of them. That's thumbs up on intermediate value theorem. It's continuous. Because it's continuous, that's totally okay. And at some point in time, you're going to hit the average between the beginning and the end. And you're going to hit that in between the two. So we're down to the last one. And it's like, well, what could be wrong with that? Because we just learned the mean value theorem. And that's what it looked like. There's a value somewhere on there where the derivative at that value would be equal to the slope of the line connecting them. That was what the mean value theorem said. But if you remember the mean value theorem, it has to be differentiable, not just continuous. So we could look at the function. And so what I tried to do is I tried to find the derivative of that function at pi over 2, and Wolfram alpha gave me an undefined. And then I graphed it on Desmos to see, and you can see what pi over 2 looks like. It's undefined there. So therefore, that's the answer. That's the one that's false, because you can't use the mean value theorem there because it's not differentiable over the entire interval. Last one. Answer is none. Because we have no indication this thing is differentiable or continuous, then we can't apply any of these theorems because it doesn't say anything on there about the function being either differentiable or continuous. So move on with our lives. Okay, that's the extreme value theorem. It's just saying if you're on a closed interval and you got two endpoints, then at some point in time, you're going to hit a maximum and you're going to have to hit a minimum as long as you're continuous over that interval, over that closed interval. All right. So now we're going to talk a little bit about increasing and decreasing functions. So where are we at? 10 minutes. Okay, we're doing pretty good. So now we're going to talk about like what can I figure out about the graph of a function using derivatives, and in this one is the function increasing or decreasing? So look at this one over here. Derivative is 0 at here and derivative is 0 there, just like it looks. Would you say it was decreasing over the entire closed interval from pi to 2 pi? Why or why not? And we get a discussion over this. And usually the class is pretty divided, somewhere between 30-70 one way to 70-30 the other way. Like it's about, like there's always a few people who say yes and there's a few people who say no, and the numbers change year to year. Because on the one hand, it does seem like it's going down the whole time. But on the other hand, if you think about the derivative is 0 here and the derivative is 0 there. So can I say it's decreasing over the interval between those two? It seems like it's not decreasing at the endpoints. It's decreasing everywhere in between. So I can see both sides of this argument, and there is an answer to it, and we're going to show you that right now, about is it decreasing over the whole thing. So here's a definition of decreasing. A function is decreasing over any interval a, b if anytime you have 2 points with x values that are both on the interval, and we're just going to call the left-hand one x1 and the right-hand one x2, and they're different points, that as long as you have 2 points, any 2 points that you pick over that interval, that the y value of the first one is bigger than the y value of the second one, then it's decreasing. So when we look at this, we say you pick any 2 points. I'll pick this one will be x1 and this will be x2. Is the y value here bigger than the y value there? And it's like, sure. So I'm going to pick 2 other points. I'm going to pick this one and this one. It still works. So now I'm going to say, what if I pick one of the endpoints? If I pick this one and this one, is the y value here bigger than the y value there? And so, yeah, it is. I mean, that's the highest point. And even though the derivative is 0 there isn't another point with a y value that big. So every single point, whenever you move to the right, you're always going to go down here, even starting with this point, because once you move to a new point on the right, it's got to have a lower y value. So therefore, and so you would discuss this, and so therefore, well, I'll write that down. Every time you move to the right, then the y value is smaller, right? If we're calling this A here, we're calling this B right there. So therefore, it is decreasing over the closed interval, over A to B. And I know some of you might say, I don't think it should be decreasing at point A. And we're not saying it's decreasing just at that point, but we're saying it's decreasing for all the points considered as a whole between A to B. Okay, that's the way it goes. If you disagreed with that, you can take it up with mathematicians somewhere.